Today's guest is Alex Kendall, co-founder and CEO of Wayve, the London-based company pioneering AI technology to enable autonomous vehicles to drive in complex, never-seen-before environments. Alex is a world expert in deep learning and computer vision. Before founding Wayve, Alex was a research fellow at Cambridge University, where he earned his Ph.D. in computer vision and robotics. Wayve is building global momentum for the use of deep learning to solve self-driving. Alex and his team are building AV 2.0, a next-generation autonomous driving system that can quickly and safely adapt to new driving domains anywhere in the world. If you want a little indication of how quickly Wayve is growing, interestingly, in the brief time it's taking us from recording to producing this episode, Wayve have announced commercial pilots with two of the UK's largest online grocery retailers, and they've closed a 200 million Series B with support from Microsoft and Virgin. Personally, I'm a big fan of Alex's work and very thankful to have had the opportunity to be a small investor in his company. Alex, welcome to the show. So great to have you here with us.
Thank you, Peter. I'm really excited to be here.
So, like so many great startups, Wayve was started in a garage in Cambridge specifically. Can you say a bit more about, this is 2017. You're starting this company. 2017 is, I would say, in AI, hiring was crazy. Every company is trying to hire in AI, still much today, but you could have taken any job anywhere. You decide to start your own company. How do you come to that decision?
It was an exciting time. I just finished an amazing Ph.D. in experience where I got to work on some of the early stages of computer vision, being able to teach robots to see what was around them, and so they could understand their environment in real time. And at the same time, we'd just seen work that yourselves and others had been doing in reinforcement learning that let machines make some really advanced decisions and problems that were, a few years ago thought that were maybe decades away from being able to be solved. And so it was this sort of intersection of these two ideas, being able to make decisions in real time and being able to understand the world around us that led to this sort of leap of thought that maybe we can build autonomous vehicles that can really make their own decisions and understand how they move around. And of course, we started in very modest ways. We did get a house, we got a garage, we had some very fun times building out computer equipment. The small bedroom had a 4 kilowatt server with 50 GPUs in it that was our heating for the whole house. We had cables going out the window to the garage. And our neighbors got very used to seeing our car drive around the block and slowly learn to drive. But it was bringing all these things together and sort of ultimately, I think the highlight of that seed stage of starting our team and our idea was being able to get a system live on the car that could learn in its own regard how to lane follow. At the time, the reinforcement learning ideas we'd seen in simulation needed tens of millions of episodes to learn to do to make decisions. And for us, getting a car, we put our car on a quiet country road in Cambridge and had it initialized randomly. So it had no knowledge about the world and set it off driving down this road. Every time it made a mistake and drove off the road, a safety driver, so sitting in the front seat, I would grab the steering wheel and correct it. And it wouldn't know what it did wrong. It would from 10 examples of that correction, it could figure out the patterns in the data that led it to be able to lane follow. And with just 10 examples over a couple of minutes of training, it could then lane follow and drive, up and down this road as many times as we liked. And so seeing a physical robot in front of us learn live and learn how to drive in the physical world, not in simulation like we've seen in sort of the video game realm, but actually embodied in the real world, for me, that was really exciting and gave us a glimpse of the future.
And so you were on the roads in Cambridge correcting this car periodically, and it's learning to drive, follow lanes. At the same time, I mean, this is very exciting, of course, but at the same time, I want to take us a little back in time, Alex. Obviously, you weren't born running a self-driving company. As I understand it, you grew up in New Zealand. Is that right?
Yes, in Christchurch in the South Island.
Growing up in New Zealand, how did you get intrigued by artificial intelligence, and how do you end up in the UK working on it?
Well, this is a long story or not so long story, depending on how you look at it. But I think it was a fascination with many different systems and machines, and a childhood growing up building tree huts, playing with Lego, making computer games, and also exploring the amazing natural world that we're lucky enough to have in New Zealand. And I think this sense of curiosity, adventure that particularly my family and my mum and dad, really instilled in me, I think set me up with the right values and principles to really get excited about growing and building this kind of technology. But it was, I think, late or early in my university days. So I went to the University of Auckland and studied mechatronics engineering. That was an amazing course because it sort of brushed the surface of mechanical, electrical, and software engineering, and was a real generalist engineering course. And I was fascinated with machines that had all of this complexity in them, and for me that was robotics. It's really the intersection of all of these different disciplines. It's a big multidisciplinary problem, not to mention disciplines outside engineering as well. But I actually started off, building and working on cars is very complex and capital intensive, and so I started off working on drones. And they were this was technology that I could get my hands on. You could build with a modest student budget, and I had a lot of fun putting together drones before you could buy them off the shelf. But we had to put together parts, program an Arduino with a basic PID controller to keep it stable. I put together one, and I used to love going back to our farm in Christchurch and chase sheep and other things around with these drones. But putting these machines together. And I think just the fascination with all the challenges, and I think it was really the seeing them do things that were just inspiring or amazing to me as a human, led me down the path of excitement about robotics. But it wasn't until, I was fortunate enough, there's an amazing scholarship scheme in New Zealand that sends people to Cambridge University called the Wolf Fisher Scholarship that I was fortunate enough to receive, and sent me to Cambridge, which was again another eye-opening experience across the world, and a completely different culture that I really relished. But I went there to study control theory and originally read and write papers which explicitly modeled out the world using analytical equations. And it wasn't until I started to read about machine learning, and in particular in the computer vision space, and get inspired by some of the people and my particularly some of my supervisor Roberto Cipola's work, that I started to see that machine learning and statistics could understand things that were far more complex than what we'd hand coded. And I think it was really coming into that field afresh. I'd never studied machine learning before, and coming into it without these preconceived biases of how things are done before really gave me maybe a head start from the get-go. And I think one thing I've been sort of referencing throughout here was this theme of exploration, and whether it was in the mountains in New Zealand or going to new places, that was really core to my life. And in particular, looking at the architecture around Cambridge, I was absolutely fascinated with the geometry and the structures of these beautiful buildings, especially in Trinity College where I studied. And so I actually got into computer vision because I found this structure for motion technology where you could create these amazing 3D models of these spaces. And I walked around the city with my phone, filming monocular video and running it on university servers over the weekends to create these big structure for motion models. But it was my excitement about that and the problem of simultaneous localization and mapping that really led me down into computer vision and robotics. It just brings back some wonderful memories about the people I got to meet and work with at that stage. But from there was when I stepped into machine learning and discovered really how we could use learning to accelerate what we can understand and develop by orders of magnitude.
From there, you started Wayve. It's going really, really well. You're building the future of mobility. But at the same time, it's 2017. Waymo's been around for a while. Aurora has been around for a while. We actually had Chris on the show in season 1. Tesla have been at it for a while, and we've had Andre Karpathy on the show earlier. And so what made you think that, there is something that is not being done yet that you could go do here, given these big efforts that were already underway?
Yeah, I was fortunate enough to spend some time, in the San Francisco Bay Area, and I was familiar with all of the work that was going on there. I'd read and was inspired by the DARPA grand challenges that kicked off this first generation of autonomous vehicles. But I mean, it was a number of things that really led us to believe that we could build something that could do more advanced things and behave in more intelligent ways than those systems could. And it was this idea of having a system that was intelligent enough. I was fortunate enough, as you say, there was recruitment processes at the time that were, that were insane. And I was able to see and demo the experiences of these traditional, classical self-driving cars, but they weren't what I'd call embodied intelligent. They weren't making decisions that was the promise of autonomy. They weren't sort of coexisting with other human drivers and doing things in a natural way. And when I go and drive around London, there's so many different environments where these cars have to interact with each other, naturally merge, engage, make unprotected turns, even nudge their way through cyclists and pedestrians. And all of these kind of behaviors need a level of intelligence that lets you understand the dynamics of the world and the complexities of the world around you. I couldn't see a route for that traditional approach to be able to bridge that gap. The more rules you hand code in the system, not to mention the cost and the complexity of engineering time it requires, but I just couldn't see, and I tried in a previous career, I tried to create rule-based systems that could try and do that. I couldn't see that happening. I was fascinated and amazed with what the machine learning world was doing. And someone very close to me once said that, in your career, and I really believe this, you need to be betting on not what's possible today, but where the trends are going. And everything I was reading and seeing and immersing myself around just pointed to the fact that this will be the future. So I wanted to be part of creating it.
As I'm hearing this, Alex, it's very interesting because a lot of people would say a more pure learning approach is going to be too hard. It's not going to work. And that's exactly why these efforts tend to have, many of them have learning for the vision system, for the perception system, but then non-learning for other parts of the system. And I remember you and your co-founder talking with me, I think it was at NeurIPS in Montreal at the time, where you're just getting started, saying, we think we can learn all the way, end-to-end learning. Can you say a bit more about that? What does it mean to do end-to-end learning for self-driving versus the typical approaches followed in other places right now?
Yeah, sure. So the typical approach for autonomous driving is one where you break it down into a number of different components. You have perception, where you extract a state of the world, where the road lanes are, where the other vehicles are. You might track them. Then you have perception, planning, where you plan how you want to interact with it, and then control, where you actually control the vehicle. You have other components like high definition maps that feed in prior knowledge about the world. And essentially you have all of these different components that sum together create an autonomous driving system. And the challenge there as well, an individual component might use machine learning. The way that they're interfaced and put together is largely hand designed through human designed interfaces. That has a number of challenges because you need to put large, maybe 30 or 50 person teams around each component. You have errors that essentially compound as you go through the stack. What machine learning is able to do is, and what the end-to-end approach is where you replace that entire architecture with one single giant neural network. And the beauty of this is you let data do the hard work. So by using data, you can train this to build representations and uncover behaviors that are more complex than we can hand design as humans. More specifically, what it means is that so we have a trainable neural network that goes from sensor input. So we have a calibrated sensor platform that feeds in sensor input that we then pass through this neural network and gives us a motion plan as an output. And we take that motion plan and we can then execute that on a vehicle in a way that's agnostic and scalable to many different use cases or vehicles or driving domains. But it's building that driving intelligence, that end-to-end neural network, which has the flexibility to really drive and understand its environment like you might getting in a new vehicle or a new city or a new domain, training that in a system that is powerful enough to learn that function that can map from sensory input to motion plan output. That's what we've spent the last 4 years building.
And it's so interesting to me that you're training this end-to-end. You said that in 2017, that's what you're going to do. And just a few weeks ago, you released a paper describing AV 2.0 and how self-driving needs to be rethought. And when I'm reading through it, it actually matches very closely with your vision you already had in 2017 of what AV should be. And so kind of curious, like, you've been thinking this for a while. What triggered you to write this up? And what exactly is this AV 2.0 vision that you're now communicating with the wider world in a very explicit way?
I think that's been one of the most interesting things over the years, is that we have had this very consistent vision for a long time. A lot of startups pivot, change, and adjust. And we've certainly learned things along the way. But what we've done each year is come back with just more and more evidence that this is the approach that will scale. And at the same time, we've seen more and more evidence from the traditional approach that it isn't scaling, that it's giving us some pilots in some very limited deployment areas, but it's not that future that we've been promised from autonomy. So I guess the reason for starting to talk more about it is I think it's really a function of the maturity of the technology. What we were doing in the first couple of years was really exploring many different approaches for how this might work. Everything from model-free to model-based reinforcement learning to imitation learning, a bunch of different families of algorithms that can produce such a system, AV 2.0. And we tried all of them and learned what worked well, what didn't work well, what might scale. And the next couple of years was really building out the infrastructure. One of the things that I have learned is that machine learning is really fundamentally a data engineering problem. It's programming by data, and building the infrastructure to be able to train the system has required a really sustained and I think, well, I'm very, very thankful for the amazing team I get to work with that has been able to build this out. It's not just a case of writing a few lines of code and training a neural network like you might do in a research setting, but it's producing the petabyte scale access of data that we have, of video data, to train the system, to run it through large distributed compute nodes and train it. That's what we then built out. Now we're in a position where we have what I'd say is a very mature prototype of the system, one that can demonstrate the full suite of driving behaviors that you need to drive in an urban environment. Traffic lights, roundabouts, stop signs, lane changing, all of these kind of behaviors. And we're really excited that we're now in a position to actually trial this, and we'll be on the roads next year in early 2022, doing last mile grocery delivery in London, and you'll be able to get your groceries delivered by one of our autonomous vans. And so with that, we see the need to go and actually communicate and share what we're doing. I think it's really important that we are able to engage with both the scientific and the technical communities and actually share what we're building, give feedback, and also leverage the collective intelligence of our entire research field to be able to push this forward the fastest, because this truly is, I think, one of the biggest opportunities and problems of our generation. And I just really want to see it realized very quickly.
Now, you said there that people might see their groceries delivered by a Wayve AI system driving a van. Can you say more about that? What exactly is going on there? Because it seems for a lot of self-driving cars, it's pure R&D. And here, it seems like we can watch it in action. And where do we order groceries to see your car deliver it to us?
Yeah, we're working with some wonderful partners here in the UK, and essentially integrating our autonomy platform into their vehicle operations. And this will allow us to start testing the ability for them to deliver groceries in a last mile setting. So the problem is really driving from a fulfillment center to your home to deliver groceries. And I think this is a really interesting first use case for our system. But of course, the way that we're building it and the way that we're constructing it is that it is a general learning framework that can really learn from all kinds of data that it gets access to, and has and builds up the intelligence to be able to be deployed on many different platforms. The other fantastic thing about working with some of these large grocery retailers is that they have absolutely gigantic fleets of tens of thousands of vehicles. And by working with these vehicles, we can also get access to the training data we need to train this. I think the recipe that we've really seen work again and again and again in machine learning is how can you get large-scale quantities of data, sufficient compute, and a large enough neural network that has the right structure to capture and model the problem that you're trying to solve. And so putting these things together and the data that we're able to capture from these fleets, I think this is what's most interesting for this. It's probably worth mentioning the nuances of the data though, because yes, you can create a bunch of supervised data where you have humans that actually teach the car how to drive directly, or you might, like the example I gave before, have safety drivers that correct it every time it makes a mistake. But the way to really scale these systems, I think, is with self-supervised learning, where you're able to learn from just very large-scale unstructured data of the domain you're operating in. And that's what we do with these fleet partners we work with. We deploy essentially our sensing platform on their vehicles and collect the data that they experience with their human driving fleet. And what that gives us is a very large-scale access to the data that we can observe how they drive, and we can learn how the dynamics of the world works, how they drive around, all the edge cases they experience every day, where we see weird and wonderful things on the road that that our fleet might not see itself. And having access to that scale of data and the edge cases and the experience, I think that's what really gives us the diversity and the magnitude of data to be able to train such a system.
Now, I'm curious when you say self-supervised. Of course, I'm wondering, what kind of self-supervised are you putting in there?
Yeah, I think the key signals that we can get, and these are things that I think the computer vision community has really come of age over the last few years, is concepts of geometry, motion, future prediction. So self-supervised learning is the concept of essentially using patterns in the data itself to learn representations that are ultimately useful for an end task. And the ones that are really powerful in the driving domain are using some of the structure of the world around us to understand motion, geometry, as well as what actually plays out in these driving experiences to be able to teach our system to predict the future. And so understanding the motion of things and how they move and interact is really what this data is well placed for.
I think what we've seen in the self-driving space, at least from where I'm sitting, I'm curious what you think, is that for a long time it was an R&D thing. And then in the last few years, different companies have claimed different first adoption cases as the one that's in some sense the right one where it should start. So some companies will say trucking, highway trucking is the thing that will be commercialized first, and that's the way to bootstrap everything else. Others have said, hey, we're going to deliver passengers, like Waymo, they're driving passengers around, right? Others, like Neuro, have said, we're going to build a very small vehicle that can, that's less likely to harm anyone because it's so small and it maybe moves more slowly. It's not a full car, or definitely not a full truck. And so you specifically chose grocery deliveries, but with a van, not with a small vehicle, but with a van. What thinking went into that?
All of these different use cases, of course, autonomy is going to address all of them, and I think really enhance each of their respective use cases. But for me, I think the most impactful and interesting use case, and the one that's really going to have the largest impact on society, is operating in urban domains. That's where most of the populations are centered throughout the world. That's where I think most of the let's say energy and transportation really exists, and where we can have the biggest impact on availability, safety, and accessibility of transportation solutions, as well as sustainability, making this whole system more efficient. So it's really a desire to tackle that hardest problem first, and more fundamentally move away from the approach we've seen in autonomous driving, which was, for the first generation of approaches, it's really trying to brute force and get something to work once. Can you pick the simplest environment, going to Chandler in Arizona, and can you get something to work once in a place where the sun always shines and you've got a very structured road environment? The problem I have with that is that you end up cutting corners and you end up building technology that fundamentally doesn't scale. So for us, going straight to ride-hailing and last mile delivery within urban environments really forces us to think very deeply about the problem. How can we design a system that really will scale? How can we build a business and a solution that will really impact and provide value to the world? So it's really from an assessment of what is the trajectory this technology is on, and we firmly believe that this is we've got a pathway that will let us address this, and also making sure that we have a system that will scale. Every decision we make as a team is based around how will we get to scale, how will we get to 100 cities first, and that's why we've started in the urban ride-hailing and last mile delivery spaces.
I think it's so intriguing, Alex, because I think if 5 years ago, we would have asked people, where do you think, self-driving efforts will launched their first services, I don't think too many people would have said, yeah, center of London, that's where it's going to be happening first, because, I mean, it's so much harder. But here you are saying that actually it being harder is a good thing. The harder it is, the better for your system to be developed in that kind of space.
Yeah, I mean, the data you get and the diversity you get is so much more interesting. We're not driving on highways where you have to drive hundreds or thousands of miles to get an interesting scenario. We get edge cases every 100 meters. I mean, you take a road out of our office and immediately there's a roadwork scenario there. Then you have a roundabout, an interesting merge scenario. All of these things are just on our doorstep. And for me, the most exciting thing is when I get out in the vehicle, every couple of weeks and see a new behavior for the first time. Like I remember the first time I experienced it, complete an unprotected turn. And just to put this in context, this system is driving on roads it's never seen before in scenarios we haven't hand-coded how it should behave. We've just shown it a lot of data. And the prevailing pattern in that data is that it should stop at red lights or it should give way to other vehicles. But we haven't told it how and what to do. It's just uncover those patterns from the data itself. And then to get in the car and see it embody those behaviors and experience it in the real world of it, overtaking a double parked car, or if it doing an unprotected turn, or navigating onto the wrong side of the road to get around a roadwork scenario when when it's safe, for it to understand all of these complex things. And most importantly, for such a small team to be able to program the full suite of driving behaviors and do that through machine learning, for me, those moments are the most special and are really exciting to see around London.
And you shared a glimpse of that with us a few weeks ago. You had a post on Twitter showing 15 minutes of driving along streets where the car hadn't been before. And what I thought was really amazing here is that, well, first, the car hadn't been there before, so I couldn't rely on having pre-mapped in detail what's there. And second, that you release a video that is a continual stream, no cuts, not just a highlight, just a stream of what happens, which to me is something we also do at Covariant, is kind of showing uncut video of systems in action is really a way for people to understand what it can do or cannot do at times, of course. I mean, it gives an honest understanding of where things are at versus some highlights. And I thought it was really intriguing because it was navigating pretty complicated traffic, and it just did it, just like you described. I'm curious, how do you measure progress? Because, I mean, those videos are great, but you need to have some more quantitative metrics too, of course. And how do you go about that?
Having the right measurement in place is so important. And if you think about what we've built, it's this giant fleet learning system, a system that can take in data from our data collection vehicles or our fleet operations, ingest it into the cloud, train on it with a curriculum that's actively evolving, validate it, and then put it back to the road. But we need an objective function in machine learning. You need a loss function that you're trying to optimize for. Now, in autonomous driving, many people tend to use miles or kilometers per intervention. But the challenge with that metric is that, well, like any reward function or objective function, it can be gamed. And I mean, there's many good examples of systems that game objective functions. I mean, some of the ones I like if you think about the concept of a robot vacuum cleaner and you give it a reward for collecting dust, it might collect all of the dust it can and get the maximum reward. Then what does it do? It could reward hack and decide to knock down walls to create more dust, therefore getting more reward, but you've put something wrong in the system. You can think of many of these kind of examples, but with driving, it's so important to get that right so that you create the right objective function that produces a system that can intelligently behave within society. For us, that's got to be the right combination of user feedback and making sure that we actually address what we're trying to enhance the humans that these machines serve to do, but also look at things on a per scenario basis. So when you think about your driving scenarios, you can break down what you call your operational design domain, how you think about driving, into different factors: the static scenario, the dynamic scenario, and the environmental conditions. And you can break down, and ultimately there are about 14,000 factors that you can break this down into if you go very granularly. Now, what we've built is a system that when you drive throughout the world, when our system arbitrarily drives, and it can drive anywhere, it's got the intelligence to drive to places it hasn't seen before, when it drives, we're able to classify at every state, every time step along that drive, where in that 14,000 dimensional matrix that point of time is. Is it going through a roundabout in the rain with cyclists beside you? We can do this through computer vision and through other databases that we have access to about things like weather, road environments, and things like that. And the ability to automatically classify each different time step we go into where it is in that operational design domain gives us the ability to understand performance at a very granular level and in a way that allows us to compare like for like. So we can compare the difficulty of routes and factor out the difficulty and actually compare. One of the things in machine learning that you can get very used to is training and testing on a static data set. In my Ph.D, I worked on a lot of computer vision data sets where you would train a model, whether it's stereo vision, semantic segmentation, classification. You'd have this static data set where you just train and test on the same thing, and you'd continually optimize that number to go up. When we go and test with autonomous driving, when we go and train our systems to drive, we might go and test one day and then go test another model the other day, and we want to know which one's better. But each time you drive, you get an entirely different set of scenarios on the road. Even if you drive the same road twice, the weather will be different, the traffic will be different, there might be roadworks, all of this kind of stuff. And so being able to classify every time step we go along into this, we can then start to compare like for like how it performs in similar environments. And if you test over about 100 kilometers for a new model, then you can actually start to get signal and compare things. Not only that, but we can target deployments to actually go out and find those scenarios. We don't, our safety driver team are really like driving instructors for our robots. We get them to go out and find the interventions, find the learning examples so that we can understand how to improve and we can learn from that signal. And so ultimately, to go back to your original question on how do we measure performance, we look at performance within a target deployment domain. We look at performance on how successfully can we drive autonomously and in a way that's both safe and trustworthy through a particular part of that operational design domain. What percentage of the time do we do that to an acceptable level?
Now, that's really intriguing. And I mean, the contrast would be maybe the standard metric that's often reported in the past is number of miles driven on average per human intervention. And that's what's, I believe, required to report in California if you're testing your vehicles in California, where a lot of the AV efforts are testing. And so this seems a much broader spectrum of evaluation that you're looking at than miles driven per intervention.
Yeah, that's right. Because miles driven per intervention, they're not equivalent. For example, if you drive within an environment, let's say you're on a highway in Arizona and it's sunny and you can see everything, you can do many miles per intervention with the same level of driving intelligence compared to in London when you have rain, you've got busy traffic everywhere. You might go a couple of blocks and then hit a scenario that your system can't drive through. So comparing these two, this metric really isn't a fair comparison between them, and that's why I think you need to look at things on a per scenario basis. And it also covers up things like teleoperation or teleassistance when many systems will just dial in and have a human remotely drive the vehicle. And I think that also covers up the driving intelligence that we're trying to design. To really unlock autonomy, you need a system that you can trust, that is safe and is intelligent enough to really enhance our lives as humanity. And I don't, if we're having a system that every tens of kilometers needs a teleassistance system to dial in, then that doesn't achieve that for me.
Now, talking about full autonomy, you said that Wayve will power some of the deliveries that are going to happen. Now, when you say that, when we would see such a Wayve-powered delivery van, is there still going to be a person in there?
Yeah, to begin with, we will have safety drivers, which to begin with will help teach our system and then validate that the system, monitor the system while we validate that it is safe and reliable and acceptably safe to launch. But ultimately, these will be vehicles that won't have humans in them. And so that also brings up another big question with what is the human-robot interaction? How do we actually get a society? How do we interact with these robots? I'm hugely excited about that, and that's where I think that there are massive questions to answer there and to learn about. If you think, one of the interesting things in autonomy for me is that why I think this is one of the most important and pivotal problems for society today is that it's the first time machines and artificial intelligence is going to have a physical interface with society, one that's not an opt-in. For example, if you wear augmented reality glasses, or if you buy a vacuum cleaning robot, those are opt-in. They're done in closed environments where you subscribe to those experiences or services. Autonomous driving, this is something that is going to be driving on the roads, and as a pedestrian on the footpath, you're not going to explicitly consent to it being there. It's just something that inherently you have to interact with and trust. And that's a huge moment in the history of technology. This is a time where we're going to have robots really going around our urban environments and society in general, and adding value to our lives in a way that we trust and enhances what we're doing. So I think that's a huge responsibility, a huge moment in history, and one that really requires a massive capabilities in terms of intelligence and behavior. But most importantly, the way we interact with these vehicles, we've got to get that right. There are going to be new behavioral norms. For example, these vehicles, while they'll be very safe, we'll need to figure out how to actually interact with people, how to load and unload groceries or parcels, or how to let people in or out of those vehicles. If people want to get out of the vehicle at any time, how do they stop safely, and how do we facilitate that experience? And then even how do you communicate? I think it won't be too long until we see a natural language interface to communicate with these vehicles. How can you backseat drive them? How can you tell them where and how you want to drive? Maybe you want to get somewhere more assertively, or maybe you're more relaxed and you want to take a scenic route. All of these kind of things, I think with technology will come together much quicker than we expect. And that for me will produce the future that we've been promised and that we'll see with autonomy.
In fact, recently you wrote an op-ed in Wired commenting on, how this transition is going to happen in the foreseeable future and what it'll entail to bring autonomous vehicles into our worlds. And the thing that really stands out to me is the question how to build the trust, how to have a pedestrian on the street feel just as comfortable, or ideally more comfortable, with the self-driving car than with a car with a driver in it. And how do you see that path to start building that trust?
I think that's trust is really important for autonomy. And for me, trust, if I think about people I trust in my lives, I think trust is built out over a long period of time of joint experiences where you meet or exceed expectations. When I break that down of how I feel when I trust others, what does that mean? I think that means that we need to be very transparent and clear with how we expect this technology to behave and what we should expect it to do for us as society. I think it means that the performance needs to be very high and we need to be accurate in what we do. I think there are a number of assumptions people usually make when it comes to trust for autonomy, and one of the assumptions is that we should be able to causally reason about what we do and be transparent in why the system is making a decision it is. And while there are many benefits to that, I don't think it is strictly necessary for trust in these systems, because I think you can get it with setting the right expectations and performing accurately to those. I think that there needs to be accountability, though. If unfortunately something were to go wrong, then there needs to be some accountability and recourse to improving the system. But you can draw many analogies here to other technologies that we trust within our lives. Like when you get on an airplane, you trust to be taken from A to B. A lot of people won't understand the actual aerodynamics of the aircraft or the way the avionics control the aircraft. But it meets expectations and it's accurate and safe, certainly in this day and age. But then I guess the difference when you think about autonomous driving is that prior to autonomous driving, it's something that a lot of us as humans do, and it's something we're very familiar with. Not many of us are pilots, but many of us do actually drive vehicles. And so we have higher understanding of that process and expectations. And so there, I think it's very important to communicate both the expectations, the value that the system brings, and then ultimately be very confident, evidence-driven in how and why the system will behave that way. I think that's a recipe for building a system that ultimately will build up long-term value. The failure modes are really where you start to overpromise, or when you start to put it in situations where it's perhaps not designed for or out of its domain. I think we've got to be very careful as an industry of making sure that we are transparent with the capabilities of the technology, and also focused on continually learning, adapting, and improving the technology as we learn more about the impact and the needs of society over time.
Now, one of the big debates related to self-driving is whether cameras is enough or whether you also need other sensory modalities to have a reliable, trustable self-driving car, right? And so I'm curious, where do you stand, Alex, and where is Wayve in the current process?
So both my personal and Wayve's position on sensing is that we are agnostic to the sensing platform that we will use. We will use the most safe and scalable sensing platform that is available, because ultimately the technology we've built can learn to drive based off data. And if you change the sensing platform, it's just a matter of getting driving data with that new sensing modality and learning to drive and learning the patterns in that data to drive from that sensor. Having said that, though, it's got to be able to scale. And for me, camera sensors and a camera-first approach has all of the visibility that you need and all of the signal you need to drive. They're passive sensors, ones that are already manufactured at scale today, and sensors we understand very well. So I think from a safety perspective, from an information content perspective, and from a scalability perspective, they're unmet today. It's not to say there won't be new sensing types that are invented in the future that can go beyond. And of course, adding more sensors strictly gives you more information. As long as your system is very good at being attentive to the right signal and can deal with perhaps a lower signal to noise ratio as you add more sensors, then of course, adding more sensors when it is affordable and scalable and safe to do so should theoretically improve the system. But for us, cameras give us everything about appearance, motion, geometry, not to mention the fact that there is a great existence proof that humans can do many intelligent things with the visual spectrum as our input alone. Many people also overlook the fact that there's inertial sensors, GPS, microphones in autonomous vehicles, and so those are important as well. But the bulk of the intelligent decision making that our vehicle makes and how I think autonomy can be scaled is with the visual spectrum.
Now, as you look at the trajectory of the company, I heard you hit some recent exciting milestones. Can you say a little bit about that?
Hey, there have been lots of really exciting things that our team has gone through this year. I could list a bunch of them, but one of them you may be referring to is the fact that one of the core promises of our system is that, and of this AV 2.0 technology, is that it can learn to drive in a way that really generalizes and really scales. And so this is something that we set a really bold mission to go and achieve and go and demonstrate this year, not just as theory, but in practice. So at the start of the year, we set out a mission to go and take this technology and demonstrate that it could drive in multiple cities and really scale. And so what we did over the last couple of months as we developed the system is we've trained and developed it on London training data. In the last couple of months, we've gone out to 6 different UK cities, big cities like Cambridge, Manchester, Leeds, Coventry, and have shown that we can drive in these new cities despite having never been there before, never having seen data from there before, not having access to an HD map, a high definition map of these cities before. And this is fantastic, right? Because this even surprised me. I thought we'd have to go to these cities and get a little bit of local training data to adapt to those new distributions. But it turns out that the neural networks that we train are intelligent enough to generalize from London data to these different types of cities. And these cities experience different weather, they have different road layouts. For example, Cambridge has many cobblestone streets. It's a university town, there's lots of cyclists around. Or you go to Manchester in the north and you get, we drove around the football stadium there and you get different multi-agent behaviors of a lot of the fans around Manchester United. And so there's many different scenarios and for us to have a system that was intelligent enough to generalize these new cities and get similar performance metrics in these cities as we see in London was really exciting. And talking about long, continuous, uninterrupted episodes of autonomy, we could see it drive for 10 minutes doing amazingly complex scenarios in the heart of these cities and do it all in a zero-shot setting without any training data actually from that city itself.
Wow, that must have been quite the feeling, because that's in some sense a full validation of everything you've been thinking of how it would go, that training in London is the right place to get your training data, and it just worked. What was the first day like when the first day you tried this?
It was a really exciting one. I remember when our operations team were absolutely fantastic on the front line with the vehicles. I remember when they took it up to the first city, to Cambridge, where we started the company. And we went and drove around there and got some early data. And I was just clicking refresh on our console that gives us access to all the data replay when the data was being ingested, and waiting for the videos coming up, looking at the experience and performance. And for me, that was hugely exciting, because you're right, it validates things that we can build a system that can learn and drive in London, and focus on getting the system to launch. And once we've done that, it will horizontally scale and effortlessly scale with data globally. And for me, that's it's absolutely validation of our approach and our ability to build autonomy for everyone everywhere.
So Alex, you have this vision for AV 2.0, which is end-to-end learning. And I think when you look at the AV space, when I look at it and when I hear a lot of people talk about it, they see it as, in some sense, maybe a spectrum, where on the one end of the spectrum, there is efforts like Waymo, where detailed 3D mapping of the environment the car goes into seems to play a big role in how the system works. And so it's a somewhat more traditional robotics approach. Of course, a lot of learning involved, but also a lot of traditional robotic components involved to drive against detailed 3D maps. And then there is, on the other end of the spectrum, according to how people seem to look at it, there is, let's say, Tesla-like approach. And there, the idea is that you don't need a map ahead of time, not a detailed map. Your cameras will take care of it for you. You'll on the fly understand what's around you. But actually, as I understand Tesla car, it'll still have many traditional motion planning and control components. So even though the vision, the perception is very learning-driven, very data-driven, there's still many other components. And so, is it fair to say that Wayve is in some sense it's Waymo is on one end of the spectrum, Tesla on another end, but actually that's not correct. Wayve is actually beyond Tesla on that spectrum in terms of bringing learning into the full decision stack of the car. Is that right?
Yeah, I think that's an accurate way of describing it, because, fundamentally, self-driving is an AI problem. It's a large-scale decision-making problem, often with partial information. And this is exactly the pattern we've seen in so many different fields of AI, whether we take natural language processing or computer vision. Over the last 20 years, we've seen this movement from handcrafting representations to learning features to then learning end-to-end, right from input to output. And we've seen this in natural language processing, we've seen this in computer vision, we've seen this in game-playing agents, and I think autonomous driving is going to be no different. So, of course, it made sense to start 20 years ago in the DARPA Grand Challenge days with a system that was hand-coded, because that was what we understood at the time. But fundamentally, the improvements that we've seen and the discoveries we've seen in the AI space now make it possible to provide a learning solution. And the benefits are really clear of that, right? We've seen learning give us the ability to understand problems that humans can't even dream of hand-coding a solution to. Let's take an example of what we've seen with AlphaGo. Google DeepMind developed a system that could learn to play the game of Go and outperform the world champion humans at this problem. Now, Go is a game. I think there's 10 to the power of 14 different permutations that you can have on the board. Now, if you can imagine building a rule-based system where you go and enumerate every single one of those scenarios, it's more than numbers than there are atoms in the universe. In fact, in autonomous driving, if you have a 4x4 pixel image, RGB image, the number of permutations you can have with that, with an 8-bit image, is also more than the number of atoms in the universe. These are really astronomical numbers. And so to be able to understand the patterns and the manifolds within this data, it's become increasingly clear that machine learning is the best way to do it. Machine learning and deep learning is the best technology that we know today that can understand these complex decision-making systems and actually generalize from the data points that we do have and we do observe. So with all of that we've seen in other spaces, in autonomous driving, we're the team that's really building out an end-to-end learning solution that, like AlphaGo, like GPT-3, like all of these game-changing models and technologies, we're building a system, AV 2.0, that can learn to drive from data. It shares, moves away from some of the rule-based systems like you described. It shares the vision of camera first and no HD maps like what the Tesla team are building, but really does go one step further and says, okay, let's also learn the way that we control the vehicle. Let's learn all the way from input to output with one single deep neural network. I think that's the future of autonomous driving.
I mean, you could argue that when you look at the human brain as a driver, that we don't have different modules we can pinpoint either. We somehow learn to drive, and there could be some analogies there. At the same time, some people will argue against it. Of course, they will say that this is not a good idea because it's harder to understand. It's harder to debug the system because it's this bigger system that does so many things in one calculation effectively. And so I'm curious about your take on that. Like, how do you make sure it's not harder to debug, not harder to understand where it's going to work, not work?
That's what we've spent a long time really trying to figure out. And while I think it was true 5 years ago to say that you couldn't interpret these systems, I think the advances we've had in recent years in ability to quantify the uncertainty of a neural network or understand where the attention lies or where the saliency of a decision is. I think some of these advances in deep learning now give us the ability to build a system that we can really understand. But ultimately, I think you need to provide a learning loop that resolves whenever you have an issue. Let's say you end up going to a traffic light and you don't stop for the red light. If you program a rule and you just say this red light at this location we need to stop, it's a bit like it's a band-aid, and I don't think you can address. It's not like these are bugs that you address one by one in the system. You need to address them on a pattern level, on what's the overall behavior that you want to teach into the system. And so what we do is we collect many examples of where the system might fail or need to be improved, and we collect all of those examples and learn from them collectively. That then lets you learn behaviors that both meet the requirements of all of the different behaviors you need to do, but also in a way that really does generalize. It doesn't give you specific, brittle design behaviors around different scenarios, but it gives you a driving intelligence that really understands the broad spectrum of behaviors you need on the road. So I think it's really those two things: the ability to understand uncertainty and quantify what the system does and doesn't know, and then secondly, looking at behaviors on a collective level rather than hand-coding rules for specific events themselves.
I really like the example you've given there with, dealing with a red light, because, I mean, on the one hand, it's a rule, you stop for a red light, that's the right thing to do. But there could be scenarios where you actually, maybe you want to scoot backwards or you want to actually slowly scoot forward despite the fact that there is a red light. I mean, imagine some car is just clearly going to hit you if you don't get out of the way. You want to move out of the way instead of staying put. And once you put in rules, it's very hard. At least I can't see how to do it. Once you have a rule that you always stay put behind a red light, it seems hard to then work around that rule again to get more flexibility in the few scenarios where that's actually needed.
Yeah, that's right. And not only that. I mean, it's so easy to think about edge cases. For example, if you see a red light, stop. But then, I mean, there's been lots of videos that are circulated online of when you are following a vehicle that is carrying a bunch of traffic lights to be installed somewhere, and those traffic lights are on the back of the vehicle, and you might be driving 100 kilometers down a highway, 100 kilometers an hour down a highway, and you don't want to slam the brakes on in the middle of this highway. There's many examples you can give like that, but really what you need is context. You need contextual understanding to make a decision. And one of the other things that you need to think about is, can you get that context if you separate out perception and control? I would argue that you can't, or at least it's not optimal to do so, because if you're enumerating all of the different features you need from a perception system, if your perception system needs to tell you where the lane lines are, what the state of the traffic light is, where the other agents are on the scene, what is their velocity, acceleration, intention over the next 3 seconds, if you enumerate out all of these different factors, then you then have a decision-making system that, yes, it can have APIs into them and make decisions based off these factors, but they might be necessary to make a decision, but I'd argue that they're unlikely to be sufficient. They're unlikely to give you the full context, and you can't make decision in isolation about all of these things. You need to make decisions in the full context. I mean, you gave the example, a great example, Pieter, that you might be in a red light stopped, but there might be a scenario where you want to go through it to avoid someone who's off course, breaking the road rules that might be coming in to hit you. In that scenario, you can't just look at the red light alone, but you need the full scene context. That's why I think it's a mistake to reason about individual traffic light scenarios, signals, or instances in the scene individually, or take signals in isolation, but you need a system that's attentive over the whole scene. That, we've just found that just gets too complex if you try and hand engineer it. And what we're able to do with end-to-end learning is pass the learned representation to a decision-making system, and the representation that we extract from the sensory input is trained from the decision we're trying to make. So it's really trained end-to-end, and that reduces that hand-coded and brittle interface, but lets us learn something that's high-dimensional and flexible to make the decisions that we need to make to be able to safely drive.
That's interesting to hear, because when I play this back in my mind, I'm hearing that once you hard code an interface between perception and control, all of a sudden you could be limited. And by letting that interface be learned, control gets access to everything it might need to make the decisions it's supposed to make. Nothing will be left out because it's learned to pass on the necessary information.
Yeah, that's exactly right. There might be things in the environment that you might not have thought of. For example, if there's a plastic bag on the road, how do you know if it's an object you can run over or not? The segmentation alone might not be enough. You might need other signals of how it moves. Or a vehicle itself, you might be able to segment it, but do you have its indicator light state? There's so many different things that make up our ability to understand the context of how a vehicle might move around in the world. And it's not just enough to know basic things about it, but you need to understand the surrounding context. So it's not just pulling out those individual factors, but it's understanding how they interact with each other. That level of complexity, I think that's where you need to learn, and the learning objective and the signal you get from that is based on what you're trying to achieve, what you're trying to control.
Right, and it's that observation that makes AV 2.0, the stack there, different from the previous stacks. There's no separation anymore between perception and control. It's learned together.
Yep, that's absolutely right.
What does it look like when you look into the future, 5, 10, 20 years from now? What do cities look like? What does the world look like if you are successful?
I think embodied autonomy, embodied intelligence, autonomous mobile robotics, I think this is going to be the next wave of computing. This is going to be as transformative as what perhaps the personal computer or the iPhone was. It's a new paradigm where we have these mobile robots that move around about the world. They're connected, they have the sensing on board to be able to make intelligent decisions and interact with us in a way that is safe, sustainable, reliable, and ultimately lets us do things more effectively. This is a really interesting world because it provides so much opportunity. It provides opportunity for us to be able to move people and goods around more effortlessly, more sustainably, but also absolutely improve the safety of our transportation in society. But in general, I think it provides this platform to be able to build levels of intelligence that can really allow us to uncover and understand more about what we do as a society and how this works. And I think this is going to be, I can't wait to see what this uncovers. I think it'll be absolutely transformative.
Well, Alex, thank you for the wonderful conversation. It's so nice to catch up. I can't wait for my chance, hopefully in the near future, to make it out to London and maybe try a ride in one of the latest cars that you have there. Thanks again for being on.
Thank you so much, Peter. I can't wait for you and for the whole world to ride the wave soon.